This is ECET273, Modern Energy, lecture number 7. Mr. Pillar again. We're going to go through one last run on some transformer topics based on Chapter 5 of the Square text and Unit 3 of the Fardo-Patrick text. We're going to talk about nonlinear loads on transformers and the K-factor, how to deal with those nonlinear loads. Nonlinear loads cause excessive current. Nonlinear loads add that third harmonic issues to us. Calculate some equivalent impedances of transformers given the percent impedance from the nameplate. Alright, so what's a K rating? K rating is used for nonlinear loads that causes overheating effect of the wiring systems and transformers and motors and generators all across the board. Before K rating, we would just derate a transformer to compensate. So basically, I'm going to use some numbers here, but let's say your load needs a 100 kVA transformer. We're just going to put on a 150 kVA transformer so you can handle that extra ampacity that your nonlinear loads would do. K-factor is an indication of the transformer's ability to deliver power to nonlinear loads without exceeding the specified temperature limits. A K4 would indicate that the transformer could handle a load that produces 4 times the normal eddy currents. We're going to talk about what eddy currents are. We kind of touched on it, but smoothed it over to give you a better look here. And what is an eddy current? So, if you recall, I had some other text on this picture before, but this line here, not only is it a magnetic flux, there's magnetic flux on the primary, magnetic flux on the secondary, and magnetic flux that goes through on the steel core of the transformer. There's actually current flowing on that. That's the eddy current. So there's current flowing through here, going round and around. When you have an excessive amount of that current, there's more than what the steel can handle, the steel will overheat. Current, resistance, heat. That's the issue. So if you have those nonlinear loads out here causing some back third harmonic issues, you'll create extra current on this produced because of the magnetic field here created on the from the nonlinear loads and increase our eddy current. So to fix that, we have K4, K9, all the way up to K50. These are kind of your standard size, and as said on the last slide, K4 can handle 4 times the rated current. So in essence, the steel is approximately 4 times larger than what it needed to be. So let's kind of go through a quick example here. A step-down transformer rated 4160 at 480, 75 kVA. We have some eddy current losses of 360 watts, which means we consider things to be ideal, right? P in equals P out. Well, not entirely, because we have to pay the piper on heat and friction loss. So this transformer, the eddy current burns up 360 real watts of the in versus the out, delivering rated load at 60 hertz. The transformer is delivering rated current, but the current is non-sinusoidal, so it has harmonic content. We talked a little bit on harmonics and what that does to create that, but here you go. Here's a list of the harmonic values across the board, percents of RMS of this non-sinusoidal load. Ignoring the non-sinusoidal load, the straight-up RMS value is down here below. The 75 kVA divided by the 480 on the secondary, and you end up at 156.3 amps. Alright, so what are the actual components of the current on the low side? Well, you take that load, IRMS, times 48%, you get 78 amps on your fundamental, 71.1 amps on your third, and you go all the way through and calculate all those percentages, and you add them up appropriately per the harmonic distortion, and then you can create the total harmonic number. What is the effect of the nonlinear load on the transformer? Well, those harmonic currents cause harmonic fluxes, and those fluxes cause extra eddy current losses. The eddy current loss varies with the frequency squared. So we get a little bit of an equation here. We kind of ignored most of the equations up until now that had anything to do with magnetics, but B is a magnetic value, K is a constant with the steel, B is a magnetic value, the signal. T is time, F is frequency, 60 hertz at this time, P is the energy caused. Higher order harmonics will cause higher eddy current losses. The question is how much higher? So we have this K rating. So we do a ratio of the nonlinear load divided by the 60 hertz load frequency. And here's the limit calculation of that. We'll go through and you plug all the values that you received on the previous table into this little equation. And that's what we do here. I'm going to assume that calculus has taught you how to do that, so we're not going to do that, but we end up with 45.6 of K rating. The eddy current losses would be about 45.6 times the actual loss, the standard given loss, and we end up with 16.4 kW. Well, that's too high. We can't derate this transformer. We can't reduce the allowable load. So we have to use a transformer that's designed for a nonlinear load. The K-factor rated transformers, they're available from manufacturers and built to withstand the effects of the nonlinear load. They're K rating. Typically they're built with thinner steel lamination, possibly a lower loss type steel, and larger conductors, especially on the neutral. So what does that mean? Well, again, we didn't talk about the magnetics. But a core of a transformer isn't a solid chunk of steel. It's laminated. It's built up, generally speaking, of thin sheets. And each sheet allows for better heat loss and better current carrying capacity as we laminate the sheets together that way. Lower loss steel, steel is simply an alloy of iron. You have a different ratio of minerals that are in that steel, and it has different characteristics: heat loss, current carrying, conducting capabilities, and across the board. Larger conductors are obvious, I believe, because the bigger conductor, the more current it can carry. Obviously, a higher K rating means additional cost, making things thinner but still solid. Fancier steel types, larger conductors, there's more copper there, it means additional cost. So nameplate ratings. We talked about our apparent power, and we talked about our voltage. We talked about how we could calculate our current on our nameplate. So we have another value that we pay attention to on the nameplate, and that would be per unit impedance. And I've talked about nameplates before, but here's actually a nameplate. We've got a bunch of things here. We have a kVA rating, a frequency, voltage ratings on a high voltage side, on the low voltage side, current ratings. They already did the math for you, but you could have done that yourself. But here, percent impedance, 5.59%. All right, that's what we're going to talk about here. Transformers have both resistive and leakage reactance. Okay, what does that mean? It costs, again, to use a transformer. P equals I times R, we assume both sides are equal. Not only do you have eddy current losses, but there's voltage drop and current loss in the actual inductors of the coils on either side of the transformer. The ohmic impedance is on the nameplate as a percent impedance. That means the real resistance. It's a unitless quality, and it's related to the actual impedance of the winding. And again, I'm talking about the real, not the imaginary portion of it. The percent of rated voltage that, when applied to the high voltage side, will cause rated current to flow in the transformer under short circuit conditions. Now we're going to do this in the lab. We're going to test, we're going to do a short circuit test of our transformer. So on the secondary side, we're literally going to put a wire from X1 to X4, and we're going to dial the voltage up on the primary until we read maximum current of that transformer. That will allow us to use Ohm's law to calculate the resistance of the transformer, and then we would give that a percent impedance. We don't really want to do that for large transformers, so they gave us percent impedance on our transformers to help calculate that value rather than empirically gain that value. So here's an example. Step-down transformer is 4160 480 75 kVA. To obtain rated winding current during a short circuit test required application of 239 volts. What's the percent impedance and the equivalent impedance? Well, so equivalent impedance is V short circuit divided by I short circuit is equal to V short circuit divided by I rated. Again, you don't want to use more than rated current in this test because you'll burn out your windings. So we go to rated current, we find a primary voltage value that takes us up to I rated, and then we measure the short circuit voltage. So I rated, in this case, 75 kVA divided by 4160K. There's your primary side of I rated. So 239 volts on the primary, short circuit voltage, divided by the primary current gives us 13.3 ohms. Alright, so what does that mean in percent impedance? Well, V short circuit divided by V rated times 100%, we end up with 5.75%. We can use 5.75 to back into this equation up here. Percent impedance divided by 100% times V rated over I rated gives you 13.3 ohms. So we can go from a nameplate value, 5.75, that was discovered empirically at the factory under safe conditions, all the way up to 239 volts on a 4160 kV transformer, so that in the field we don't have to do that to get this calculation. It's percent impedance. So why use percent impedance? Well, transformer Z's limit fault current during a short circuit. So basically what happens is, if for whatever reason on the customer side of the transformer there becomes a short circuit, well, the impedance of the transformer limits that current. And so here, that's a good thing. That helps you size fusing and whatnot. A step-down transformer is rated 4160, 480 volts, 75 kVA. We have a 5.75% impedance. What's the maximum fault current? So the maximum value of fault current we're going to end up to get, derived off this equation, I rated divided by percent impedance divided by 100. So we find our I rated of the secondary, because that's where our fault current is going to happen that we care about. Primary current is what the utility is going to care about. 156.3 amps. 156.3 amps divided by 0.0575. We end up at a fault current of 2,717 amps. Alright, so what we're talking about in this condition, if we had a short circuit, we could experience as much as 2,700 amps through this area. So again, we don't want to see that, but allows us to know the flashpoint capabilities, arc fault issues, fusing, sizing, and all that across the line to find using that Z equivalent and that percent impedance. Typically, your percent impedance is somewhere between 4 to 7% for power transformers. So that means we're somewhere between 14 to 25 times the I rated. K rating of transformers are used to compensate the excessive eddy currents due to nonlinear loads and those pesky third harmonics. Percent impedance is a unitless specification on the nameplate of a transformer, and that is what I have for this. Thank you for paying attention.